Hi, my name is Suraj. I am going to talk about investigation on the role of coherence in polarization beam combining of 200-watt fiber lasers. Beam combining is an attractive method for power scaling of laser sources, especially when power from an individual laser beam is saturated due to different nonlinear effects. So in those methods, polarization beam combination is a relatively straightforward approach. The basic schematic diagram of polarization beam combining setup is given, where two orthogonal polarizations are combined together using a polarization beam splitter. In this work, our investigations focus on modeling of polarization and phase fluctuations and role of coherence in two beam polarization beam combining, and we will validate the simulation result using 200-watt amplifiers. The basic schematic diagram of a polarization beam combining setup is given here. In polarization beam combining, a polarization beam splitter is used as in reverse direction for combining two orthogonal polarizations. So here beam A and beam B is directed towards the PBS and combined together. So here we have outputs coming through two output ports since the beams are not ideal. In an ideal case, the only output will be ICT. Since our beams are not considered ideal in this case, we will be getting some intensity in the dark port also, which is represented by IDT. For calculating the intensity coming to each port, we will first consider the electric fields coming to each port. So here A of t and B of t are the fields coming to the main port, where rho p represents the polarization extinction ratio of the beam splitter, and rho 1 of t and rho 2 of t represents the polarization beam extinction ratio of the incoming beams. Phi 1 of t and phi 2 of t are the phase of each arm. Similarly, the electric fields at dark port also can be represented as given here. Please note that if rho 1 of p and rho 2 of t are ideal cases, like if the value is 1, then we will be considering linear polarization. Since it is not ideal one, we are considering a general case where a mixed polarization coming as the input. So intensity can be calculated as summing up the fields and squaring them. The equation for main port intensity is given here. The intensity at the dark port also can be expressed as given here. Please note that the equation contains two parts, one involving phase difference between the beams. If the beams are uncorrelated, the term involving phase difference will be 0. We have simulated the previously mentioned mathematical model by considering electric fields E1 and E2 constant and unity. We have considered the noise in the individual beams contains 10 Hz, 100 Hz and 1 kHz components. Also we have done it for different values of PBS extinction ratio 20 dB and 15 dB. So the main port simulated time traces are given here for both correlated and uncorrelated case. We can see that there is no significant change we can observe here. The dark port intensity time trace is also simulated for correlated and uncorrelated case. Here we can see some significant change in the noise when the beams are uncorrelated. We have plotted the mean intensity and standard deviation of the output for both main port and dark port. So we have plotted the mean intensity for different values of PBS extinction ratios and two different values of beam polarization extinction. Also we have plotted this for correlated and uncorrelated cases for comparison. So we can see that there is no visible difference in the mean intensity even the beams are correlated or uncorrelated. In the case of standard deviation also, there is no visible difference we can observe. The mean intensity increases with the PBS extinction ratio because when PBS extinction ratio increases, the PBS is going into more ideal one. So next one is dark port results. Mean intensity shows a different trend with increase in PBS extinction ratio. That's also expected because when the PBS extinction ratio is higher, the PBS is more ideal one, so the power going to the dark port will be decreasing. Here also in the case of mean intensity, there is no much difference when they are correlated and uncorrelated. Also, if we check the standard deviation of the outputs in the dark port, that shows a difference. So for the uncorrelated case, we can see that there is a significant reduction in noise. So that is because the component going to the dark port is mainly coming from the fluctuations, the polarization fluctuation of the beams, and due to the non-ideality of the beam splitter also. The DC component going to the dark port is minimum. So the noise due to the fluctuating components will dominate in the output. That's why we can observe more change in the noise level when the beams are uncorrelated. These are the dark spot results we simulated with incorporating the phase noise extracted from our CBC experiments. CBC means coherent beam combining. So here also you can see that when beams are uncorrelated, there is a significant reduction in noise level. That is expected from our previous results. Now we are going to the experimental part of this work. We have directed two nearly linearly polarized laser beam to the polarization beam splitter by the help of mirrors. The main port power is observed in the power meter, and the time traces are observed in the dark port by the help of another beam splitter and apertures, and also a photodetector. We have a feedback loop also in the setup for phase control, which is going to the fiber part of this experiment setup. For simplicity, we have included the fiber part in the diagram. We have observed the main port power using a thermal power meter. We can see that in both correlated and uncorrelated cases, we have similar powers coming to the main port with 98% efficiency. For making the beams uncorrelated, we have mismatched by a length greater than the coherence length of the laser source we have used. So we can see that there is no dependence of coherence in this main port power levels, and noise levels also look similar. These are the time traces we recorded for both correlated and uncorrelated cases in the dark port. As we have seen in the simulation results, here also we can see that there is a significant reduction in noise level when the beams are uncorrelated. So these results will agree with our simulation results. In conclusion, the effect of phase and polarization fluctuations on the two beam polarization combining has been studied in detail with simulations. Our studies show that coherence has an impact on the stability of polarization beam combined output due to imperfection in the polarization exchange ratio of the two beams and the PBS. Polarization beam combining with the 200-watt fiber lasers with 98% efficiency has been demonstrated experimentally, which well agrees with our simulation results. I am thanking everyone who supported this work, and thanks for watching.